if we extend the previous belt warning example by adding more inputs, like the one previously we have KPS, now we have KPS TD, 5 inputs. Now the previous memory with 8x1 memory system and lookup table, that becomes inefficient as we have more inputs. So 3 inputs, only 8 words required, and now we have 5 inputs, so we require more words. So what we do is we split our circuit into smaller parts, so that 3 variable can map to one memory, and the rest 3 inputs map to the other memory. So now we require two 8x1 memory systems. If we have 8 inputs, we require 256 words, and if we have 16 inputs, we require 536 words. So FPGA does have enormous small lookup tables. We break our circuit into small lookup tables. If the circuit has more input, more must partition circuit into smaller parts so that they can map up to the smaller lookup table. For example, we have extended the seatbelt warning light system over here. Now we require 2 lookup tables to map this. The first lookup table is implementing k dot p dot s dash, and the second lookup table is mapping x dot x plus t plus d. So you can see 3 inputs are going to first lookup table, and the output of this lookup table along with two other inputs are going to the second lookup table. So in this way we have implemented the partial truth table in the first table, lookup table, and the rest truth table into the second lookup table. So map to 3 inputs LUT. We have mapped the 5 input circuit to 3 input LUTs like this. So you can see another example over here. In this example, we have 9 input circuit. So if we have 9 input circuit, we require 2 raised to 9, which is 512 words. Rather, we have another approach. We break the circuit into smaller parts, 3x1, and then map them to a smaller memory system. For example, 3x1, 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 and then again we have 3x1. So we can map this this circuit into 4 8x1 memory lookup tables. So partition, firstly we have to partition our circuit into 3x1 lookup tables. Now instead of 512 words, we are required 4 memory lookup tables. 8x1 memory smaller than a 9 input lookup table with 512 word. Let's see another type of lookup tables. In this, LUT typically have 2 or more outputs, not just one. So we can implement more than one function with the help of one lookup table. So you can see this function F, which has 4 input AND gate first, and then an OR gate of 2 inputs. So how to map this function using 8x2 memory system? Firstly, we have to break the AND gate into 2 stages. First AND gate is a 3 input AND gate ABC, then its output is T. Then we require a truth table for T dot D plus E. So firstly we will be giving the truth table of A, B, C into the first lookup table. You can use either of the two inputs, D0 or D1. Over here we are using D0. So D0 is given at A2, and then A1 is D, and A0 is E. So we will be burning the truth table of this into the second LUT, and you may use either of the two inputs again. We are use either of the two outputs again. So we are using D1 over here. First column unused, second column implements AND. So in the second column unused, and first column implement AND or sub-circuit. So this is how we can utilize the lookup tables. one column of each lookup table is still unused, we can implement some other function with the help of this lookup tables. Okay, now we want to implement the circuit of a 2x4 decoder to a 3 input 2 output LUTs. Since we have 2 output LUTs, so decoder has 4 outputs, so we require at least 2 lookup tables for this implementation. So you can see in the figure, D0, D1, D2, D3 are the outputs for the decoders. How to implement this? We will be giving I0, I1 as an input to both the lookup tables. You can see over here the the most significant bit of both the address bus are given 0. So that means we are utilizing the upper half of the truth table. So D0 is equals to uh, 1 0, D1 is equals to 0 1, and when there is input at I1, and then we have 0 1, and D2 is 1 0, and D3 is 0 1 at the place number 3. So this is how we implement the lookup table for the 2x4 decoder. So you can see over here, when I0 and I1 are given 0 0, only D0 will be given 1, and rest of the outputs will be 0. Similarly, when we give 0 1, then D1 will be 1 and rest of the outputs will be 0. Giving 1 0 will make D2 1 and rest output 0. Similarly, 1 1 will make D3 1 and all the other outputs will be 0. This is how the decoder works and implemented using 3x2 lookup tables, 3x2 lookup tables. Okay, let's see what are the FPGA internal structures of a switch matrix. The previous example, we have hardwired connection between the LUTs. The output, if we want an output to go to the other LUT, we have hardwired it, but in actual we have a switch matrix. What is a switch matrix? We want to program the connections between the two LUTs in such a way, if we want output from the previous lookup table, we can give it to the input of the next lookup table, or we want some other input, it can also be directed to the LUT inputs address buses. So use switch matrix, also known as programmable interconnect. What are LUTs? They are simple mux-based version. Each output can be set to any of the 4 inputs. You can see we can give 2 of the inputs, or we can switch between 2 inputs and 2 previous LUTs outputs. So any of the these 4 can be directed to the next LUT's input, and one output is pair, which is the third output. So 2 lines are programmable and one can be given as an separate input. So each output can be set to any of the 4 inputs just by programming its 2-bit configuration memory. So let's see how the mapping of 2x4 decoder is done on FPGA using a switch matrix. In the previous we have seen we require 2 inputs, both I0 and I1, both inputs go to both LUTs. We do not require the output from the previous LUT. So in the switch matrix, the input connections are given at M2 and F3. We do not require M0 and M1. So at M2, so the first input goes from M2, which is the second third input. So we will be giving 1 0, and the fourth input M3 1 1 will be directed to the next input. So in this way, we have directed the 2 inputs to the A1 and A0 of the second LUT, and A2 the unconnect and the input which is not connected to your LUT is given 0. So in this way, we have programmed the switch matrix in such a way that the inputs are mapped to the address lines instead of giving them hardwire. Map the extended seatbelt warning lights into the FPGA switch matrix. So first three inputs KPS are going to the first LUTs. So we are using the D0 output of this, and that this will be directed to the first to the next LUT. So the first bit, the first connection of the switch matrix is 0 0. Then we require two other inputs. We require one X and one T from the input. So T is directed to the second LUTs by giving it T is connected to M2, so 1 0 is given to the switch matrix. So in this way, X and T are directed to second input and A2 is given 0. So the D0 is used over here. Both the D0's column are used over here, which will be implementing W. By far now we have implemented only the combinational circuits, combinational logic from the LUTs, but we can also implement sequential logic from LUTs by adding a flip-flop at the output of each output. So now the LUT along with its flip-flop is called configurable logic block, CLB. CLB is equals to LUT plus flip-flop. We can program the CLB output to come from either a flip-flop or directly from the LUTs. If we want a combinational circuit output, we can program the CLB flip-flop so that the output is directly given out, and if we want a sequential circuit, then the output is clocked with a flip-flop so that it becomes a sequential circuit. So you can see the figure with the over here. It has a LUT and each output D1 and D0 is wired with a multiplexer through a flip-flop and directly. So if we give 0 to the flip-flop, then the logical output is coming out, and if we give 1, then the sequential output is coming out. So a 1-bit CLB output configuration memory is given over here. So it is a 8x2 memory block with the CLB of the FPGA is shown over here along with the switch matrix. Switch matrix is choosing whether the input is coming from the previous LUT or from the new input. Okay, let's see an example in which we have you can see at the left side in which we have 4 flip-flops. The output of the flip-flops are W, X, Y, Z. W is A dash, X is B dash, Y is C, and Z is D. So we have 4 inputs over here and 4 outputs. So we need 8 cross. If we have 8x2 memory, we need 2 CLBs for this, so that we can have 4 outputs. So you can see two CLB blocks over here. The input to the first CLBs are A and B, and the A2 is given 0 of both the CLBs because we don't require them. We only require 2 inputs, A and B to the first CLB and C and D to the second CLB. So what is implemented inside the memory? D1 is equals to the D1 is W, so W is equals to A dash. So A dash is given in the first column of CLB, and B dash is given in the second column of CLB. So X is equals to B dash, and C and D. To configure the switch matrix, we can see we require C and D at the inputs of the second CLB. So first block of switch matrix is given 1 0 and second is 1 1. So it is forwarding C and D to the second CLB input. A1 and A0. Now y is equals to C, so C is written in the first column and D is written in the second column of the second CLB. So in this way we are getting four outputs W, X, Y, Z according to the figure. You may note over here the outputs are we are getting the output from the flip-flops. So all the all the CLB's flip-flops are given one, so that to implement a sequential circuit instead of a combinational circuit, because our original circuit has flip-flops, so this we require sequential circuit. So these are the steps for reducing the implication table. The first step is mark state pair having different output as non-equivalent. Across all the state pairs which are having different outputs, they cannot be equivalent in any case. States having different outputs are obviously not equivalent. Then mark each unmarked state pair, write the next state pair for the same input values. You have to make pairs for the same input and give the next state of them. Make the state pairs for every unmarked state pairs. Then third, for each unmarked state pair, mark state pairs having non-equivalent state next state pairs or non-equivalent. Repeat this process until no change occur or until all the states are marked. States with non-equivalent next state for the same input value cannot be equivalent each time through the step is called pass. Merge the remaining state pair. Remaining state pair must be equivalent. So draw the reduced state table. Let's take another example of this state reduction by implication table. We have been given a state diagram. This is similar to that we have done earlier. Let's draw a implication table, and step number one is mark all the state pairs having outputs that are not equivalent. So S0 is only a state which has a different output than S1, S2, S3. So all the states of all the pairs of S0 with others will be cancelled out as shown over here. So do it step by step. Then step 2 is for the given FSM on the right, mark the state pairs having different output as non-equivalent. And step 2 is for each marked state pair, write the next state pairs for the same values of input. So for S1, S3, S1 and S3, when x is equals to 0, the next state pair is S0 and S2. And when x is equals to 1, the next state pair is S1 and S3. For S1 and S2, we have S2 and S2 and S1 and S3 when x is equals to 1. For S2 and S3, we have S3 and S3 for x is equals to 1, and for x is equals to 0, we have S2 and S0. So these are all the state pairs, next state pairs for the same values of input for the unmarked states. Now we have done the state 1, which is mark all the state pairs having non-equal outputs. Then step 2 is for each unmarked state pair, write the next state pairs for the same value of input. Now we are going to do the third state pairs. For each unmarked state pair, mark state pairs having non-equivalent state pairs for non-equivalent. We have to mark all the state pairs which were previously marked as non-equivalent. So we have seen that S0 and S2 was non-equivalent, so that's why the state pair S1 and S3 also becomes marked cross. Then S1 and S3 has been marked cross, so in the next iteration S2 and S1 will be crossed, and S0 and S2 was previously crossed, so we will cross the S2 and S3. So you can see in this state diagram all the state pairs becomes crossed and there are no state left which are not which can be equivalent, so all of them are marked crossed. This is from your book, example from a book. We have a state diagram which is now having more states and looks like more complex, so it's not easy to visualize them and see which are equivalent or non-equivalent. So we will reduce the state diagram using implication table only. So we are going to draw the graph. At the x-axis we have S0, S1, S2, S3, and at y-axis we have S1, S2, S3, S4. The pairs above the diagonals and the diagonal pairs are removed and we are left with the graph over here. Firstly, we cross all the states which have not equivalent output, so they are not equivalent. So state pair S0 is not equivalent to S1 and S2. Similarly, S4 is not equivalent to S1 and S2, and S3 is not equal to S1 and S2. So these have been crossed out as shown over here. Now step number 2 is we have to write the next state pairs of all the states which are uncrossed. So take time and write the state pairs for the next states. So for S0 and S4, what are the next state pairs? S0 and S1, S4 and S2. For S0 and S3, we have S0, S1, S3, S2, S1 and S2, we have S3, S4, S2, S1, and for S3, S4, we have S0, S0, S4, S3. We have to go through one more iteration and see if any of the state pairs was previously marked cross over here. So S0 and S4, any pair, look over here. We have seen previously that S2 and S3 are not equivalent, so S0 and S3 also becomes not equivalent, it is crossed out, and S2 is not equivalent to S4 also, so it is also crossed out. S3 and S4 can be equivalent and S1 and S2 can be equivalent. Similarly, S3 and S4 can be equivalent and S0 is always equivalent to S1. So these are not crossed out, so we are left with two boxes, which is so from looking over here, the state pairs which are uncrossed over here can be equivalent. So S1 is equivalent to S2 and S3 is equivalent to S4. So we will reduce the state diagram over here. You can see we will merge remaining state pairs. So S0 is the only left pair which is not merged. S3 is merged with S4 and S2 is merged with S2. We will reduce it and redraw this the state diagram with all the inputs and outputs over here. So S0 is having output as y is equals to 0, S3, S4 is having output y is equals to 0, S1 and S2 is having y is equals to 1. Complete the graph. Now there can be state diagrams which can be too big. Table for large FSM can be too big for human to work. For example, n input, each state pair can be 2 raised by n. Next state pairs for 4 input, 2 raised by 4 is 16. Next state pairs. 100 state will be nearly 1 lakh state pairs. So there must be some other method to reduce the states. We need automation. So the state reduction is done by software using automation, often use heuristic to reduce computing time.